Okay, we're starting. What's up, everybody? What's up? Yeah, we got all. Let's go. Okay, sorry I started a little late. I'm bad with technology. I've done this like many times, but I still forget how to do it. We'll probably start. We'll say start at 7:20, so it's 7:16 right now. If you're watching not live, which you probably aren't, sad. Make sure you skip 4 minutes. Okay. Yeah. No one's on the live stream. There were 2 people waiting, and then like. Oh, well, no. Well, I told them. Oh, you're one of them.
Yeah, I was waiting because I was like walking up and I was trying to like see if you were starting up.
Yeah.
I'm good.
Okay. What if like here? Wait, can I try something? Oh, that's really weird. Oh.
You just broke the matrix.
Yeah.
So today,
What are you doing on my live stream?
teaching math.
Yes.
I don't know what we're learning, but
No. I don't think anyone does, right? It's a surprise, like always.
Yeah. I'm gonna be surprised. Well, the only way to prepare is to take a look at all the problems and the solutions of previous exams, so that way you can be prepared for today.
Exactly. All you have to do is look at every single Putnam problem that has ever been, happened.
No, every math problem.
Yes.
Yeah.
Right.
If you look at enough
No,
math problems,
I can't
then they won't be able.
that was really rude.
See every math problem.
Dude. This is the most fun I've had at the beginning of the stream. Usually it's just me in my room, just like sad.
All it took was a second computer.
Okay. I'm so prepared. So I don't know. I hope I'm prepared. Yes, I told them. We'll start at 7:20. This mask is too loose. Last session, my mask was way too loose, and it was just.
How many times have you spun that around?
Oh, like so many.
You wonder why it gets loose.
Yeah, I know.
Have you ever considered getting a new one?
Yeah. Well, I mean, I have a lot. I just don't like to rewear them. I like them to be clean. All right. It's okay. We'll see. Okay. Okay. Let's get started. So first, I'm going to give an overview of what this is. So this is the final Putnam review session. The Putnam exam is this Saturday. Now, this is the consolidation of, actually, wait, how much was it? 234 hours of study, of deep focus and study on the Putnam exam. Well, right. And I have kind of, through all of this experience, I have kind of summarized all of my main ideas and tips that I would give you to make you a better problem solver. Okay, so this is going to be applicable broadly. This is not just going to be about the Putnam exam. Of course, kind of my motivation for doing all of this is not just because of some exam, right? To be a better problem solver. But really, if I had to, the way that I organized all of this, there's going to be 3 overarching principles. Okay, so those are like 3 big takeaways. If you only took those things away from this, that would be, fine. So 3 overarching principles. And then the main body of this, there's 3 sections. Okay, and each of these sections will, should I talk about this now? No, yeah, I will. So there's 3 sections to this thing. This is basically a big document that I have that I put together. So the first section, quality of mind. Wow. Okay. I was going to use the word mindset, but I feel like that was kind of overdone, so I decided to make it fancy. And there's 11 sort of sections for this, subsections. Common fallacies. Is this readable? Kind of. Common fallacies. There are going to be 9 things I'm going to talk about there, and approach. And there will be 16 points for that. So there's 36 sort of total that I've come up with. And then at the end, I'm going to talk about some common techniques, like some that are more math-based. This is going to be very abstract and kind of broadly applicable. But at the end, I'll go through some common techniques for more mathematical things. But anyway, let's just get into it. So let's begin. So first, I'm going to talk about these overarching principles. So these are kind of some of the really big, important ideas big takeaways that you should have from this. So the first one, last year when I did this, I only had 1, but I've come up with 3. So the first one, let me look at this, is, sorry, I have a lot of different things. Okay, so actually, you know what? I'm gonna use different color markers. This is the first. I know this is the first. This is a big moment. Abstraction must be supported by concreteness. I'm like black pen, red pen. Okay. Yeah. And analysis must be supported by action. And I'm going to explain what I mean by these things. So this is the first thing. This is sort of super important. Okay. This is, at least obviously I'm biased. I think it's important because I made it up. But I'm going to explain what each of these statements means. So first, abstraction must be supported by concreteness. So what that means is here, let me look. So a lot of times in a Putnam problem, you're asked to solve something for the general case, general n. But if you're going to think about the general case, you should be supported by a concrete example or set of examples. So instead of just diving in to solve some problem for general n, you should test cases like n equal to 5, n equal to 3. I mean, of course, it kind of depends on the problem. And before you abstract the problem to sort of make it abstract, you should have concrete examples to set yourself up to be able to do that effectively. So in short, I guess I'll erase both of these. So in short, test cases and observe. Okay, so when you test cases like when you have a problem for a general n and you're testing cases, really what you're trying to do, the case testing is not just done blindly. Okay, so because ultimately abstraction and pattern recognition, making observations, these are all the end goal. The end goal is to solve it for the general n. So when you're testing cases, you're trying to be as observant as possible about what's going on. You're not just doing a computation. You're trying to look at what steps am I doing to get to that computation and what things will generalize. But the thing is, tackling like the nebulous general case without having a concrete point of reference or multiple concrete points of reference is very difficult. So this is one of the reasons I put this first is because this is a big mistake I made. So for the first exam, basically for a very long time, I would kind of ignore the case testing component, and I would always try to tackle the very abstract general case from the beginning. But this is a bad strategy, right? As I just kind of explained, you need to have concrete points of reference. So, all right. So now I'm going to talk about the second one. Okay, analysis must be supported by action. Now I know I said I had 3. Technically, both of those are part of the first one. It's not really the structure. Okay, so here's a life lesson with Stephen Arndt. Okay, so here's a common issue that a lot of college students face, including myself. Okay, which is what do I want to do as a career, right? Or maybe what do I want to pick as a major? So for some people, especially maybe if you're here, you already know what major you want to be. Most likely a math major. I know that's not true in general, right? But I think that everyone has kind of considered what they want to do as a career. And here, let me try to use this analogy. Oh yeah, so for myself, so I wasn't really sure. Over the summer, I was really thinking about whether I wanted to go into industry and get like a tech job or go into research, like go to grad school. So I was really split between doing these 2 things. I wasn't sure which one I wanted. So I did a lot of analysis on which of these, I looked online, like what is each of these about, what is it like, blah, blah, blah. A lot of analysis. But eventually what I realized is that the best course of action to figuring out which one I want to do is why don't I just try to get an internship and try to get a research position, do both, and see which one I like. So the point is that, at many stages in a problem, you're going to be presented with a lot of different choices. And it's important, like a set of different paths that you could take. And it's very important to analyze these choices and attempt to pick the most promising one. But sometimes you have to recognize that sometimes taking action, just picking something and testing it and seeing how it goes is often a better strategy than trying to analyze it from the outside, right? So analysis is important. Okay, so you do have to think about, here are my possible choices, which one is best. Analysis is important, but it's much more informed when it's supported by action. Okay, and this is like a broad idea, right? Okay, so that's the first sort of overarching principle. Abstraction must be supported by concreteness. Analysis must be supported by action, right? Now the second thing is that you want to focus not only on the math, okay? But also on the psychology. There's a very big psychological component to the Putnam. And this is something that I'll also discuss a little bit more later. So let me again explain what this means and elaborate a bit. So the Putnam is not just about being good at math. It's also about being good at focus, right? And being good at sustained focus and the right kind of focus because it's such a long exam, right? So now, there's different types of focus, okay? At least that I kind of, how I see it. And the right kind I call deep focus, and I'll explain what that means. Okay, deep focus. So this is also taken from a book like Deep Work by Cal Newport. If you read this book, it's a very good book. This is sort of adapted from that. So the question I'm going to ask, and I want everyone to think about, is what does it mean to be focused? Or when you think of someone who's focused, what do you visualize? And I would say most people only envision one type, which I will call, so there's 3 types that I've sort of characterized. Most people only think of one type, which I call hyperfocus. Now, an example of when you might be hyper-focused is if you have an assignment due in 10 minutes, It's 11:50 p.m. You have an assignment due in 10 minutes, right? You are completely focused on something, but you're also very tunnel visioned, right? And you're really trying to optimize for speed over actual like, I don't want to say you're optimizing for speed. So like, or another example, like imagine solving 100 2-digit by 2-digit addition problems as quickly as possible. Okay, so a bunch of very simple addition problems as quickly as possible. So you're writing quickly and you're thinking very quickly, and you're optimizing for speed and agility. But let's say you encounter a 2-digit by 2-digit multiplication problem on this exam. Then you're kind of like, you're in like an unstable state of mind. So you're very easily distracted and you're not very resilient to obstacles. Okay, so if you imagine plowing through addition problems and then you hit a multiplication one, you're going to be thrown off balance very easily. Okay, so the idea is you're going too fast and it's difficult to maintain control when you hit a bump. And so you also have very poor stamina. So you cannot be hyper-focused for a really long time. You can't be completely, I guess like another way to say this is laser focused. You can't be laser focused for like 3 hours, okay? And so you burn out. So this is not good for the Putnam, right? You do not want to be in this state of mind for the Putnam because you're not trying to do easy problems quickly. You're trying to do hard problems slowly. So the second is moderate flow. So has anyone heard what the flow state is? No? Okay. So the flow state is basically like if you've ever been working on an assignment or a task and time kind of passes quickly, you're very focused on the task and it kind of feels good. Like if you've ever been just like spontaneously like productive for 2 hours, right? That's the flow state and it's very nice, okay? And moderate flow is like the type of focus you should aim for on most of your assignments, right? But and it's not very effortful, which is something that is kind of a pro and a con. Because what it means is that you have very high stamina. If you're like, because like, you know, a lot of times like, you know, you can be productive for like maybe 2 hours and it like feels good, right? You're in the flow state, you're in the zone. But it's also difficult to get like deep key insights in the state of mind because you're not applying that much mental effort, right? And it also can be unstable. So like something minor, if you've ever been in the zone, something minor can take you like out of the zone and then it can be hard to get back in, right? So the third type is what I call deep focus. And this is the one that you want to aim for on the Putnam. So it has all of the important characteristics of moderate flow. So you're kind of in the zone, but you're not feeling rushed. But the best way I can describe this, it's kind of hard to describe, is that it optimizes for openness. The biggest emphasis is on being mentally open, okay? And like, I guess one way you can visualize this is like, it's kind of ironic, but you almost feel like your head is completely empty, okay? And it's kind of ironic. But the idea is that in this state, you're very receptive to your own ideas from your subconscious, okay? So you're like in a state of listening to yourself, right? Your own ideas, letting them come forward, and then you're able to analyze whether they're fruitful or not, okay? So deep focus is like a state of listening, like you're trying to listen to yourself, okay? It's very weird, but deep focus is also strong and resilient. So it's best done in a quiet, isolated environment, but if, you know, there's a distraction in that environment, you're not easily thrown off, okay? So it's like you're in the zone, but you're also very stable. Like if something external were to come in, then you wouldn't be distracted. So deep focus is a very abstract idea, and it's something I'll return to frequently. Like my best succinct description is that your mind feels like as open as possible. You're like instead of trying to generate ideas for how to solve a problem, you're listening for ideas, okay? And if you become distracted or tired, you're able to return back to equilibrium, okay? All right, so that's very abstract. Okay, so let's, thinking of basically, I think the idea that don't try to generate ideas, try to listen for them, right? All right, so now the final overarching principle. So these things are like probably the biggest, like this is like the summary, right? The third overarching principle is that you should let your intuition guide you shoot. Oh no, oh no. I'll get that later. Guide you, but remain skeptical of it. So this was really the when I last did like this big review thing. This was the only like overarching thing I had. And I'll really explain what this means because this is also really important. So intuition is part of your subconscious brain, okay, and it's built through experience. So like, so basically, like the way intuition works is like the more you encounter like something that's you've seen before, right, similar problem, then you like you become better at like finding solutions without having to consciously think about them, right? So like if I showed like when I first, maybe when you first learned how to integrate x squared, okay, if you know how to do that, okay, when you first learn how to do that, you have to like think about the power rule, right? Or like differentiate x squared, for example, okay? When you first learn how to differentiate x squared, you have to think about the power rule. But once you've seen it so much, you can just do it really intuitively. And it's not just about memorization. Because if I showed you x to the 997, you've probably never seen that before, but if I told you to use power rule, you could do it right away, if you've had a lot of experience. Another thing is like, you have intuition for like a lot of different things. Like you have intuition how to eat food, right? Like you don't have to think about eating food to eat food. If you think about eating food, it's actually a very complex process, right? So I'm kind of belaboring that. So now the thing about your intuition is that it's very good at giving you a broad idea of what to do, but it's not very good at handling specific details or nuances. Okay, so this is very important. So let's say that you see a cat. Okay, I'm more of a dog person, so this might be biased. But let's say you see a cat, right? Your intuition tells you that it'll probably be very unfriendly, or that it likes to keep to itself or sleep in cardboard boxes, for example. Okay, right? Like the moment you see that cat, that's what you think. Well, at least if you're me, okay? So, and your intuition is probably correct in a broad sense, right? Those stereotypes about cats are broadly true, but you can't classify all cats as being the same, right? So you get that initial intuition, and you should absolutely question it when you first get that, right? Because it's not able to account for those fluctuations or nuances or details. The same is true of Putnam problems. So a lot of the initial ideas you get for a problem are going to come from your intuition. In fact, all your ideas come from your intuition in a sense. But you also have to remain skeptical of those ideas because they might not be able to account for the nuances of the problem. So this is a good way to, approach a lot of things, in my opinion, right? Including politics, but I'm not going to talk about that. So, all right. So now I'll go through each of the three sections and talk about each of the points. So those are really the most important broad things that I can talk about. So here, all right. So first section has to do with mindset, basically. Okay, quality of mind. Okay. First is to relax. Okay, relax. So rushing in general does not actually save you time. Okay, so especially on a Putnam problem. So rushing a Putnam problem does not save you time because a lot of times you're moving at high speeds, but over much longer distances. Okay, so what that means is a lot of times you're taking an inefficient path to the solution. So if you take your time, you will most effectively use it in the process. Okay, and this is a life lesson with Stephen Arm. Okay, if you take your time, you're going to use it most efficiently in the process. And another thing that's important is that quantity does not constitute progress. Just because your proof is 15 pages long doesn't mean that you made a lot of progress on the problem, right? Don't conflate the amount that you've written or done with the actual progress you've made, right? So often a lot of progress is going to be you can make on a Putnam problem from a very single idea that's very small, right? Okay, the second thing is the psychological component. So again, all of these things have to do with your mindset, okay? Or they kind of pertain to that. So the Putnam is difficult, not only because it uses very advanced and technical math, okay? But also because of the psychological challenge that comes with it, okay? Like the students who take the exam, they care very much about their math ability, and they're usually taking math tests that they're doing very well on because they're all usually good math students. So like the Putnam exam is unforgiving in its ability to generate like self-doubt, okay? And that only clouds your view when you're trying to solve a problem. Okay, so if you're like thinking like, oh, I suck at math, like during the Putnam, then that's mental resource. That's like part of your mind that you're dedicating to something extraneous that you could be actually using to solve the problem, right? You know what I mean? So that's something you have to recognize. Don't beat yourself up if you're not able to solve anything, because most people are not able to solve anything. All right, so third is be comfortable with unfamiliarity. So when you open the exam booklet, okay, or like when you're first solving a problem, or wait, let me look at this. Oh yeah, you may have very little idea of what is actually going on, or how the structures in the problem work, or how to start, okay? And most people, when they open the Putnam exam, they see the first problem, they have zero idea what to do, okay? This is completely fine. So you have to basically embrace this, okay? You can't be frustrated if you don't know what to do, because most people don't know what to do. When you're comfortable with unfamiliarity, you're much less likely to jump to conclusions. So a common thing that can happen is if, let's say you see A1, you have no idea how to do it, and that makes you nervous or insecure, then you may be very hasty and let's say it's a true or false, and you conjecture that it's true when actually it's false or something like that before you actually looked at the problem. And then that's a whole nother thing. Like basically you're trying to prove something impossible, which is a huge waste of time. So the point is, if you're comfortable with unfamiliarity, you're not going to jump to conclusions as easily, and you're not going to be like as nervous to reach a solution. So, okay. The fourth is prime your intuition. Okay, so this is not like math prime. Okay, this is like the verb prime. Yes, that's a verb. I just needed to make sure, you know. You need to make sure. Okay. So this is all about maintaining an organized environment around. So you want to maintain an organized environment, okay, in 3 places. So around you, obviously that's what most people think about, organized around them, on your paper, and in your head. Okay, the last 2 most people don't think about. You want to stay organized in all those 3 places. It also includes taking proper like recovery measures and relaxing through the problem-solving process. This is something I'm going to talk about later. So like, you know, sometimes you may hit a dead end and you may get frustrated. So priming your intuition is all about like, I mean, it kind of has to do with a lot of these things. So this is vital to remaining as creative as possible. And all it requires is just maintaining organization. So the idea behind this is that, like, if you're in a very organized environment, you know, like you're mentally organized, your paper is organized, the environment is organized, then your intuition is going to be much more receptive to your own ideas, right? Like if you ever try to think about 2 things at once, it's really hard, right? So this is kind of about clearing your mind as much as possible, right? So that you can get the most out of yourself mentally. Okay, so the 5th thing is to, well, you know what? I'll rephrase it. Mental stable equilibrium. Okay, this is also important. All of these, well, obviously I think all of these things are important. Mental stable equilibrium. So what does that mean? So this is something that I've thought about and made. Someone else has probably thought about this. But basically, one issue that can come with organizing your environment, okay, is if you become like OCD about it. So let's say that you have a perfectly organized environment, then you're perfectly sort of set up to be as like focused in the right way as possible. But if there's a distraction that happens in that environment, you can't let that completely distract you and like tank you, right? You can't your focus needs to be in like a stable equilibrium. So any distraction that happens, you're able to return back to being focused, as opposed to just becoming unfocused, right? So like if you've ever seen like those pictures online of like unsatisfying photos or something, it's like you have like maybe a lot of dots that are like this, and then one is like not properly placed. I bet no one on the live stream can see that. And it's like this is like if this happens in your environment, you can't let that really distract you. You know what I mean? You have to be able to return back to mental stable equilibrium and be focused. Okay. All right. Trying to get through these. So, all right. So first 5 down. So the 6th one, and there's no really specific order. I just kind of did it randomly. So the 6th one is remaining open through breakthroughs. All right. So the idea with this is when you're solving a problem, if you are able to, like a lot of times, or not very frequently, but you'll get a key idea. You'll have like a breakthrough in the problem. Like, oh, if I do this, then I can do this, and then this, and then I can solve the problem. So you have this moment where you have a breakthrough, and you sort of get a little excited, right? And a very common tendency when this happens is to rush to the solution. Okay, because you're like, oh, I figured it out, and then you just go as quickly as possible and like kind of rush to the solution. But this is very problematic because a lot of times, see, the breakthrough is part of your intuition, right? When you have a breakthrough, you have a broad idea of what to do, but you haven't actually worked through all the specific details and all the minor complications that could happen, right? So a common thing that happens, at least that happened for me when I was first studying, is that I would get an idea. I was like, oh, I know how to solve the problem. Then I rush to the solution, and then I hit a roadblock, right, or multiple roadblocks. But now I'm not in a proper state of mind to like solve them because I was rushing, right? So once you start rushing, then you're not mentally open anymore, right, and receptive to new ideas. So the point is, another way I can phrase this is, there's a very large gap between the moment you get a breakthrough and the moment you actually have the complete proof written down. Most people think once they get the breakthrough, boom, they know how to do the exact proof. That is not the case. There's a very big gap, and you need to be very careful when you're traversing that gap. Okay. So never assume that you've completely got it. Okay. You often have a lot more work ahead of you. Okay. So the next one, I might have lied. This might be 10 total. So realizing your mistakes. So realizing your mistakes. So after you make a mistake, whether it be logical or computational, take a break from that problem. This is what I would recommend. So, for example, an example of a mistake is you have a breakthrough, and then you write a lot of stuff down, and then you realize later on that actually your breakthrough was not correct, like you made a logical mistake. Okay? My tip is to take a break. And to emphasize recovery. So a lot of times it can be very frustrating. And remember, the entire time you're trying to stay as open as possible. So once you realize your mistake on a problem, it's going to be very hard to just immediately return back to the problem and like get over it right away. Okay. So emphasize recovery and make sure to stay fresh. Okay. So like once you realize your mistake, you assess like, okay, how mentally fresh am I? Like, am I good to go to continue working on this problem? If you're not fresh, you should not keep working on that problem because you're just going to be like bashing your head against the wall. Okay, remember these problems you're not trying to bash out these problems for the most part. You're trying to look for key insights, right? And put pressure to rush aside. So a big thing that happens is if you make a mistake, then you feel like you've wasted a lot of time. So you feel a lot of internal pressure to rush, which is bad. You never want to rush. So that's one of the reasons that taking a break is like a really good thing to do here. Okay. So 8. Mitigating mental sludge. Okay. So when you if you ever worked for a very long time and you get mentally tired, like at least for me, I feel like there's like almost like mental sludge. Like I'm not as like sharp as I was before, right? Or as open. And frustration, like when you're getting frustrated with the problem, and when you get tunnel vision with the problem. So tunnel vision is when you see a solution and then you only pursue that solution and you don't look for anything else. Tunnel vision. These things can create this mental sludge, okay? And they can hold you back from seeing the problem with fresh eyes. So it's possible to recover from this, but it can be difficult to recover. Like once you're mentally tired, it's hard to return back to freshness without taking a break, right? So basically, it's vastly important that during the exam, it's a long exam, that you're very aware of your level of freshness, and especially when it begins to decrease, okay? So mental sludge is like the biggest thing that holds you back from thinking clearly. So it's vital that you address it, right? So if you feel mentally tired on the exam, and I'm going to talk about this later, it's important that you don't want to just keep like bashing your head against the wall. Okay, so 9 has to do with sleepiness. Okay, you ever get sleepy? Okay, sleepiness. So how do you manage sleepiness on the exam? Okay, all of us have gotten sleepy in class. Well, I assume, right? Has everyone gotten sleepy in class before? Okay. All right. So how do you manage this? So the first thing, obviously, is get good sleep the night before. Okay. Or at least try your best to. So if you have some trouble falling asleep sometimes, that's okay. Just do your best to get good sleep. Okay. Another thing is to take it easy. So, and this is actually broadly applicable if you're ever sleepy, like during the day, right? You want to take it easy. So you don't want to like push too hard. You want to kind of relax a little bit because you're sleepy. And the thing about sleepiness is that it can actually be beneficial in some way to your state of mind. So if you're sleepy, then a sleepier mind is a lot slower. And so often you have the you have to mitigate the tendency to rush, right? But a sleepier mind kind of does that naturally for you. So if you're sleepy, you're less likely to rush, which is actually a net positive. Although, of course, being sleepy also kind of clouds your vision, so it's not like sleepiness in general, I'd say, is not good, but it can actually help you. Another thing for sleepiness, another subpoint is change environments. So if you're ever feeling sleepy, get up, right? Go get a drink of water, go to the bathroom or whatever. Change your environment. Like a lot of times, I'll be like in class, or at least especially in high school, like I'd be in class and I'd be like falling asleep, and then immediately when I like go to get a drink of water, I'm like awake. You know what I mean? So that's my advice. Okay, and the last one is this the last one? Yes, this is the last one for this section. Go to the bathroom. Go to the bathroom. Okay. So when you change environments, changing environments is arguably one of the best ways to gain more clarity. So often when you're feeling like mental sludge, when you go to the bathroom, you can actually you change your environment in general, you feel a lot more mentally open, because you've been in the same location for such a long time, right? So you don't even actually need to go to the bathroom. You know what I mean? You can just go. No one's gonna actually, if you're in there for 10 minutes, no one's gonna actually check if you're taking a dump. You know what I mean? So, but those 10 minutes can be very productive because let's say you have an hour left on the exam. Let's say you have an hour left on the exam, right? Then it's much better to have 50 minutes of, clear thinking as opposed to 1 hour of like sleepy thinking or rushed thinking, right? So if you take those 10 minutes to go to the bathroom to clear your head a bit, that's going to be very productive time, right? And it's also really good for taking a break. So you have no built-in breaks in this 3-hour block for the Putnam. So I would advise you to create at least one, right? Don't overdo this, obviously. Like, don't be in the bathroom forever. But another thing is like this applies in general too. If you don't take a break, then the break will take itself. Okay. So this is like if you've ever like a lot of times, sometimes if you plan too much for yourself one day, like I'm going to be so productive today, I'm not going to take any breaks, then the break is still going to take itself. Okay. So yeah. All right. Anyway, I kind of belabored that one. Pretty simple. Go to the back. Okay. All right. So time-wise, okay. All right. Doing okay. So the second section. So that was the first section, which had to do with mindset. So all of that is about staying mentally clear. And again, one of the things that I want to emphasize too is that all of these things, they're not just about the Putnam exam, right? These are things that apply in general. And that's why I think the Putnam exam is very valuable because it teaches you a lot of things. It teaches you how to focus better and be a better problem solver, which are like super important things in my opinion. But anyway, so the second section is common fallacies. And there's 9 points. Okay. So I have a whole big section dedicated to common fallacies that you may make mentally during the exam. Okay. So the first one is practicality versus abstraction. Now, the reason I put this first is because this is a mental shift that I made this year. Okay. So, like this really is basically just saying like this has to do with abstraction must be supported by concreteness, right? So it's this difference between like when you're looking at a problem. I used to look at the problem and try to think about it super conceptually and abstractly and all this, but sometimes it's best to just think practically what is going to work, right? On like a ground level. And so, and also like practicality is basically like case testing, right? I mean, this is like one of the things that's case testing, super important, okay? Case testing is vital to effective abstraction. This is something I already talked about. All right. The second one is never underestimate difficulty. And again, hopefully it makes sense that these are common fallacies. Like a common fallacy is to underestimate difficulty. All right. So never underestimate the difficulty of a problem. Otherwise, so like let's say you look at A1 and you're like, I know how to do this so easily. Like, this is an easy problem. I know exactly how to do this. If you underestimate the difficulty of a problem, then you're not going to apply as much mental effort to actually try and like reach the solution. And often you're going to make a lot of naive mistakes in your problem-solving process because you're not thinking that hard. And you'll become frustrated when the result doesn't come easily. Okay? So like, I think has everyone had this experience? I think so. Like, let's say you're doing your math homework and there's a problem that you look at and initially you're like, I should know how to do this. But then when you start working on it, right, like it proves to be harder than you expected, and it's very easy to get frustrated when you're not able to figure it out, right? So, so every problem's difficulty is subjective. Okay, so A1 is not necessarily easier than A2, necessarily easier than A3, etc. Okay, and the same is true of the B section. So you might be able to solve a problem that not many other people solved, and you may be able to not solve a problem that many other people did, right? It's completely subjective. So, I mean, not complete, but like, so this is natural and like to be expected. And don't beat yourself up over not being able to solve a problem when you feel like you should be able to. When you feel like you're starting to beat yourself up, that's when like you should kind of take a break. And also what you need to realize is that what's stopping you from actually solving that easy problem is a poor approach and a negative mindset, not actually your own ability, right? That's like now you've created this obstacle where you're beating yourself up, and now like that is what's stopping you from getting there. Okay, so 3, never overestimate difficulty. So this one is about always saying, hey, this problem could be hard. This one is about saying, hey, this problem could actually be easy. And again, I don't want to say easy for Putnam problems, but so one of the things this point here I put because I read this document from the Putnam test makers, okay, who are all professors. And one of the things that they said was that they do their best to try to order the problems in the level of difficulty. But professors are very bad at understanding what undergraduates actually know and don't know. Okay, like because they're like math professors have taken so much math, they don't actually know what most, you know what I mean? They don't actually know. So for example, the order is usually about right. It's not completely random, obviously. Okay, A6 or B6 probably going to be hard. Okay. One of the important takeaways is that you shouldn't be afraid of big numbers. Okay. So a common fallacy is fear of big numbers. Fear of big numbers. So, for example, I'll give a very good example. The 2015 Putnam exam I took for practice last year, and it was a very, very hard exam. Okay, probably one of the hardest in the past 10 years, or maybe the hardest. But what the top 500 cutoff was like a 13 out of 120. Okay, usually it's like 20 something. It was like 13. What I later realized, right, was that despite this exam being really hard, like A1, A2, B1, B2, all of them were harder than usual. B4, which is usually a very difficult problem, was surprisingly easy, okay? Because the professors who wrote B4 didn't know that most people knew this one trick, okay? I'm not gonna get into the problem, but basically, it was easy, okay? It should have been like B1, okay? It should have been like A1, all right? So don't let these big numbers scare you. So sometimes they're misplaced. However, of course, don't also get cocky and think that, like, in general, yeah, B4 is going to be really hard. Like, don't think that, oh, yeah, you can just solve anything necessarily. Okay. You want to be aiming for mainly, you want to be looking at A1, A2, B1, B2, maybe A3 and B3, usually. Okay. But take a look at those later problems and seriously give them some effort for a couple minutes and see if maybe you can actually make progress. Even snagging 1 point out of 10 on those problems puts you in the median, right? Okay, so 4th thing. Do I want to talk about this or am I going to talk about this later? No, I'll talk about it. Simplicity and reachability. All right, simplicity and reachability. Now, Putnam problems are hard. Everyone knows that. But that doesn't mean that they're necessarily long, okay? So what you have to think about is the people who score the highest on the Putnam exam, they're usually getting about 100 to 120 points out of 120. So they're solving in 3 hours, they're usually solving 5 problems on each section, at least, okay? What that means, and they have only 3 hours per section. So what that means is when they solve A1, they were able to solve it and write the proof in probably 15 to 20 minutes max, okay? And write the proof. So if your proof for A1 is 15 pages long, or even 5 pages long, then you're probably not looking at the simplest solution. Okay? You know what I'm saying? Like, what that means is, for every problem, there exists a direct and a straightforward solution. Okay? So you should approach this with a degree of skepticism, because some problems do require you to bash it out a little bit. But the vast majority of the time, you're able to get to the solution with only a few key steps. Okay? And sometimes the solution is going to be more on the surface than you think. So never neglect taking simplistic approaches. Okay? Don't think that you need to do something really complicated to solve a problem. Okay? And so reachability, I won't talk about reachability, just simplicity. Okay? Now, at the same time, if you know how to solve A1 using a 10-page proof and are getting 10 points, sometimes it's like, screw it, like you should just do that, because you have 3 hours in the exam. If you solve one problem, that puts you in a really good position. So that doesn't mean that like a long proof is bad, but you should never convince yourself that like, oh, this problem is stupid because it took me this long to do it. Like, no. Some people are able to do it in like 10 minutes. All right. So Dr. Fedorov, he's able to do this. I actually, the Putnam, I have to erase that. I took the Putnam seminar last year with Dr. Fedorov, and he made some offhand comment. He wasn't trying to be cocky or anything. I mean, he's Dr. Fedorov, right? He made some offhand comment like, yeah, I looked at A1 and I wasn't able to get it in like 5 or 10 minutes, so it was really hard. And I was like, bruh, you know what I mean? Anyway, so we basically judged Putnam problems as being hard if you couldn't get them in like 10 minutes. Okay, so 5 is, oh, I'm really pushing this up. Approach analysis fallacies. Oh, that one's really, like, that's probably overly complicated. Approach analysis fallacies. So basically, when you're doing a Putnam problem, you will generate many ideas for how to do something. Sometimes only one, but sometimes 2 or 3. There are 2 or 3 paths that you think of, like, I could take these 2 or 3 paths. Now, you want to analyze these paths and pick the one which you think is the most fruitful. Okay? But there's a lot of fallacies that you might make when you're doing approach analysis. Okay? So the first one, well, the first tip is to emphasize action. So I talked about this earlier, right? Instead of trying to, if you want to figure out, oh, what major do I take? Like one thing I hear a lot of people say is like, oh, like, I don't know if I'm going to like CS. I don't know if I'll be good at CS. Like, instead of trying to figure it out, why don't you just sign up for a CS class and see how it goes? You know what I mean? So the difference between, instead of just analyzing things from the outside, take a little bit of action and see how it goes, right? Emphasize action. Second thing is confirmation bias. All right. Is that even readable, like, at all? Oh my God, it's kind of small. That's okay. All right. So confirmation bias. So a lot of times when you look at a problem, or sometimes you'll look at a problem and you have an immediate gut instinct for what you should do. Okay. So you want to be very wary of confirmation bias when you're analyzing these approaches. So a lot of times you have this initial gut instinct, and then you think of, oh, but I could do this and I could do this. You're going to be, a lot of times you'll be inclined to go for that gut instinct, right? But you want to make sure that you're looking at each objectively, okay? So be careful that you're not, that your analysis of which is going to work is as objective as possible. Okay. One other, okay, actually, this is kind of interesting. So let's say you have 3 approaches that you think of, and the first one was your gut instinct, right? Then one way that the way that confirmation bias works is you're analyzing which of these is best. But because you already think that this one is best, you subconsciously put more mental attention on that one. So you direct more mental attention to this one than the other ones. And then you're like, oh, that one is the best. It's confirmation bias. Okay, it's like a self-fulfilling prophecy. All right. Okay. Okay. So The sixth one is be explicit. Okay? Be explicit. So, again, all of these, in my opinion, are pretty important. This one is important too. So, be explicit. So, be explicit about which assumptions you've made and which conclusion you've actually reached and how much generality you've maintained. Okay? So, a lot of times, you'll have an intuitive idea of what to do. Or like you have an intuitive idea of what to do. And an intuitive idea of how something works, but you need to make sure that you're explicit in like, okay, what things am I assuming? What have I actually proven? Right? Have I proven what I set out to prove, or have I proven something else? Right? So pause it, like whenever you're doing this, make sure you're not making any untrue or illogical assumptions. So a lot of times, like it can be easy to make these untrue or illogical assumptions, like they can creep into your analysis because the problems, like they can be very subtle, right? Because these problems are hard. And this is also like, this is really like meta, okay? This applies not only to mathematical results, but also to your problem-solving process, okay? So you also have to think about the assumptions that you're making in your approach analysis and in your problem-solving process. And you want to keep those in check too. But that's super like abstract. Okay, so 7, be very wary, okay, of losing generality. Okay, so, and if you decide to lose generality, a lot of times when you're, let's say you have to prove something for all rational numbers, sometimes it's useful to think about, oh, what if I just prove it for all integers, right? When you lose generality there, you do it explicitly and it's very clear that you did that, right? But a lot of times, like you may say, like let's say that, you do a test case, n equal to 5, and then you see a pattern, and then you immediately extrapolate that to the general n case. But maybe the pattern that you saw only applies if n is a multiple of 5, for example, right? So you're assuming more generality than is actually there. And you need to be very wary of doing that, because then you're going to write an incorrect proof, and you're not going to get, you're going to get max 2 points out of 10. Okay. So it's always important to track, what are the assumptions I'm making, even seemingly minor ones, because even if they're wrong, they can have huge consequences. They can totally sabotage, like your, solution, and they can also waste a lot of time and energy. So basically, really, I could summarize this, just say be careful, right? Just be careful. Okay, 8 is the must-know fallacy. This is something I also coined. Okay, I bet someone else has thought of this though. The must-know fallacy. So the must-know fallacy. Let me use an example. Okay, so this is a very common problem that I think demonstrates this well. So let's say I give you this problem: x plus y equals 5. X minus y equals 3. Find x squared minus y squared. Okay, so how would you solve this problem? This is the first time I'm taking input for the crowd. I should do this more often, because otherwise it's like I'm just talking all the time. But anyway, how would you solve this problem, Riley?
Difference of squares factorization. The right side can be broken up into x plus y times x minus y.
Right, exactly. And actually, let me, I'll rewrite this. So, 15. Here, so let's say it's like this, and you want to find x minus y. It's the same idea, right? So difference of squares factorization, so this has to be 3, right? A very common thing, a very common fallacy people will make if they first see this is that they say, okay, I need to find x minus y. So I need to find x and I need to find y. And then I need to subtract them. But you don't actually need to do that, right? You can take a shortcut. You don't need to find x and y. You only need to find their difference. Okay? So this is the must-know fallacy. So the idea that if I need to know this, then I must know this. Not always true, right? So often you assume that you need to precisely know this like specific quantity, but actually you can find this other quantity, okay, which suffices. So this fallacy is it's like a form of jumping to conclusions, right? So you're jumping to the conclusion that you need x and you need y individually to find x minus y. So one of the reasons like this is obviously, I think this problem demonstrates it well. Like if you try to solve for x and y, you get a quadratic equation. It becomes kind of gross. I don't even know like
X is 4 and Y is 1.
Oh yeah, that's actually really okay. Well, that's bad. The number should be gross. It should be like 14 or something. Okay.
Yeah.
But like yeah, so I guess you could just guess it. But like the approach to solving the quadratic for each one individually is way longer than doing this thing where you factor, right? So this happens a lot in Putnam problems where like there's a really long approach to get a solution, and then there's like a quick one, right? Okay, so 9. This is the last one. Okay, for this section. Okay, 9 is the breakthrough formalization gap. Okay. It's not that big. It's okay. The breakthrough formalization gap. Okay. So once you've made once you've made a breakthrough for a problem, or you have some big realization, a lot of times you think, okay, boom, I have the solution. I have the full complete solution. But the truth is there's a much wider gap between breakthrough and formalization than most people initially will assume. So basically, the moment that you have a big breakthrough in a problem, you need to immediately recognize in that moment that you're a decent distance away from actually getting the full solution. Okay? And sometimes you actually have many more breakthroughs that you need to make to get there. So if you neglect this mental tendency to be overconfident, then you're going to be tunnel vision, you're going to start rushing, and later you'll be frustrated when you get stuck, right? So there's the breakthrough formalization gap. There's a big gap between when you have your key idea and when you actually have the full solution to the details. Okay. So the third and final section has to do with approach. So this is kind of miscellaneous, okay? So it has to do with your approach to the exam. And I think it's a little more exam specific. So approach. And there's 16 things here, but they're smaller. Approach. So the first has to do with intuition, okay? Your intuition is a really big deal when you're solving these problems. So as I discussed, let your intuition guide you, but remain skeptical of it, right? Let me move this forward. It often cannot account for key ideas or like key details. So another thing about intuition is that case testing, like I guess this is one thing I should really emphasize. Case testing. So case testing is a really good way to build more intuition for the general problem. Okay, because as you get more experience with like n equal to 5, n equal to 6, n equal to 4, as you get more experience with these cases, then you have more experience with the problem, and then you're able to kind of like generalize it more easily. So 2, reaching a contradiction. So let me look at this. Yeah, okay. So if you're doing a proof by contradiction, you have to be careful. So whenever, I think like in general, like when you do a proof by contradiction, right, you're usually making a conjecture for what you believe to be the contradiction, right? And then you're trying to show that it indeed produces a contradiction. So basically, a lot of this has to do with like when you're making a conjecture in a problem. right? I conjecture that this is true or that this is false. You have to be very aware that that may not be the case. So you never want to make a conjecture that like if you see the pattern 1, 2, 4, and you immediately assume the pattern is 2 to the n, and you immediately conjecture this and are like, this has got to be it, right? Don't do that, because it might not actually be the case, right? You never want to conjecture something wrong and become so tunnel visioned on it that you don't because then it's just bad, okay? So here you say, okay, I conjecture that this is 2 to the n, but I'm also completely aware that it might not be, that I might miss something, right? So you have to be very careful that what you conjecture is that you're humble, okay, with what you say. I didn't really explain the contradiction. Okay, I mean, all the stuff I wrote for this is super abstract, so it's not really helpful. So I'm going to skip that one. All right. Now, this is guiding questions. Guiding questions. You know what? This is so important that I'm going to make my whole, you know what? I got multiple boards I'm going to use them, okay? Guiding questions. Yes. This is also really important, okay? Guiding questions. So whenever I solve a Putnam problem, if I'm solving it for real, okay, I always ask 3 guiding questions, okay? So if you ever look at my paper for when I do a Putnam problem, the first page, the first top half of the page is just words. There's no math, okay? So the first, and they're actually sets of questions, okay? So the first has to do with structure. So you're given a problem, and the questions here are going to pertain to the structure of the things in the problem. So basically, what do the structures in the problem look like, and how do they behave? Okay. I'm going to write that down. And of course, I mean, what do they look like? Oh, they look like that, math equation. No, that's not what I mean, right? I mean on a conceptual level. How do they behave? Okay, so this idea of function behavior we've all heard before. You can think of behavior as this very abstract idea of a lot of things. The second has to do with the condition of the problem. So you can, very roughly split the problem into, here's this given information, here's the condition that has to be true, prove why that's true, right? So the first question has to do with the structures in the problem, the given information. The second has to do with the condition, right? Basically, you ask, why would the condition be true or false? Right? What is it about this problem that makes it true or false? And also, what gives? Okay, what gives? Okay, why? Why? Why is this true? Why is this false? Also, it's a Putnam problem. Another good question you ask is, why is this interesting? Okay, because Putnam problems they usually have something interesting going on. So another question you can ask about the condition is, why is this an interesting condition? What are the subtleties that are here, right? And the third, now this is a misnomer, okay? Because the third is not a question, it's just a statement, okay? The statement has to do with simplicity. It's a reminder, okay? The reminder is, this is what I write. I will test the simplest ideas first. And a few key ideas will lead to the solution. So this is a reminder to myself to A, test the simplest ideas first, okay? And B, remember that there is a solution that relies on only a couple key ideas, right? So this is to get myself to remember you don't have to bash this through, right? Sometimes you can bash through a solution, often not, right? So with these three questions, now this one isn't a question, okay, but this is just a statement. This is kind of how I prime myself for the problem. These are the three things that I'm thinking when I start a problem. And I don't copy these explicitly. Like you, whatever the problem is, you fill these in. Like you ask, like, if it's about a function, you'd say like, what does this function look like? Whatever. It's not like a very explicit format. And also, there's also not necessarily this big distinction between structure and condition, because sometimes it'll tell you like, evaluate this expression, and it's like this disgusting math expression, right? There's not really a condition there, but you can sort of split it into these two categories, where the first has to do with the structures in the problem, the second has to do with like the end result, or something like that. Okay. So before I've done any math, these are the things. Basically, the way that you want to start a problem is by asking questions, because, like I said before, to get your ideas, you're not trying to generate ideas. You're trying to listen for them. So here, when you ask these questions to yourself, you're much more mentally primed to listen for the answers, right, from yourself. Super weird. Okay. So, okay, and then when you begin, right? When you begin the problem, it gets again wacky. Okay, I'm using multiple boards. So when you begin the problem, the first thing I always say is, let's test small cases. Okay. Let's test small cases. Okay, and then I might say, make observations. That's so not readable, is it? Oh my God. Okay. So I'd say, let's test small cases, make observations, and search for patterns. Okay. So that's the first, so the guiding questions are at the beginning. These are putting in context what you're trying to look for, right? And then, but the very beginning of the problem, you want to test small cases, okay? And make observations, look for patterns. These tell you what patterns to look for, kind of. Yeah. So this is how I start every problem. If I'm doing it like for real, okay? If I'm kind of just like doing it like not super seriously, then I might skip this, but not otherwise. Okay. The alternative approach, instead of doing something like this seems like a lot of, there's no math here, okay? The alternative approach is you just look at the problem and you're just like, oh, I have an idea, let me just do this, and then let me just do this, let me just do this. You're not actually like set up to think about it broadly, and you're not set up to think about multiple ideas. You're not set up mentally. You're just kind of like walking in the dark. Okay. All right. Anyway. Okay. All right. So, do I want to skip that? Okay. Yeah. So the next thing is about specific questions. So these questions are very broad, very abstract, okay, and are very big picture. But you also want to ask specific questions about what's going on to basically make observations and find these patterns. So like let's say you're case testing n equal to 5, right? Actually, wait. So this is a lot of fun. Okay. For specific questions. So let's say you're computing something for n equal to 5, or you're doing analysis on this case, and you make some observation, right? You notice something. Okay. One of the first specific questions you should ask is this particular thing going to apply in general, for example? Okay. or when will it apply, right? So that's like a specific question you're asking about the specific thing that you just saw, right? About your observation. Okay. So, number 5. 1 hour 15. Oh my God. Okay. Quickly. So, number 5 has to do with case testing. Okay, case testing. So, the first thing is case testing scope. Okay? So initially when you're case testing, it's probably not readable, but I just said it, okay? Case testing scope. Initially when you're case testing, you're doing very specific things like n equal to 3 or 4 or 5. You're doing very basic cases. So let's say you have to find, oh my gosh, okay. So let's say that you have a problem which is like prove for all real numbers this thing is true, okay? Then the first thing you might do is think about, okay, let me prove for all natural numbers that it's true, okay? That's my first case testing. You know what? You might even say, let me prove it true for n equal to 2, okay? Just one value and all of the real numbers, okay? So all the natural numbers. Then as you continue to case test, then you say, okay, what about all integers? And then you say, what about all the rational numbers? And then you say, what about all the real numbers? Okay, so you're always kind of case testing, right? But as you learn more about the problem, you widen that scope. Okay, so you always start from a really basic case, and then you gradually widen that scope until you're able to see what things should be like in general. And case testing throughout. Okay, so case testing is not just this thing that you do at the beginning of a problem. This is something that you use repeatedly. Okay. So case testing throughout. So even after, like you do case testing till the end. Okay. Well, I mean not always, but like you can. Like even after you make your big breakthrough. Okay. When you're trying to clarify details about a problem, even after you've subconsciously felt like you're at the end of the solution, case testing, even at the end of the problem, is still useful to clarify those details. Right? So I'm saying case testing like 100 times. Case testing is something that you should use throughout the problem. It's not just something you do at the beginning. Okay? Oh my God. Okay. All right. I'm getting people are in the chat. All right. So now I think, you know what, I'm probably going to skip a lot of these because these are all like, oh yeah, so okay, the 6th one I've talked about, the big picture, okay? So don't try to prove the big picture before you've got the sufficient pieces in place. Okay, so you always want to be thinking about the big picture in the back of your mind, but don't just try to tackle the big picture before you've, done the work, okay? Skipping that one. Okay, I forgot what number I was on. I think 6. Okay, so the intuition formalization process. All right, so the intuition formalization process. People are blowing up the chat. Okay, the intuition formalization process. So the idea with this is that intuition drives formalization and formalization drives subsequent intuition, okay? So what does this mean? What this means is the process for how you go about a problem will often look like this. So you do initial case testing, then maybe you have an idea for a pattern, right? So you have a breakthrough. Then once you make that breakthrough, okay? Wait, did I write that right? Yes. Once you make that breakthrough, you want to formalize what you've just thought. So you want to make sure that you've really clarified, like, okay, I have this abstract idea of how this is supposed to work, before you move on to the next stage of the problem, make sure that you're pretty clear on the details, right, of what you just said. So, because once you become formalized, so once you have a breakthrough, then you formalize, you organize. Remember, like I talked about earlier, being organized in your head, on your paper, right? That's going to drive subsequent intuition. So, a lot of times solving a problem is about intuition, searching for big ideas. Then you get an idea, then formalizing that idea. Then you're, the next stage, and then you kind of repeat that process. Okay. Oh my God. Okay. So the intuition and formalization process is like this back and forth, okay, between these two things. All right. So, okay, this is a good one. I mean, Okay. Pinpoint and fix. Pinpoint and fix. So, what is this one? After you get stuck, the first step to fixing any hole is to pinpoint what that hole is, okay? So, like, a lot of times, if you're doing a hard math problem, you might get stuck, but very rarely do you really think about what is it specifically that is getting you stuck, right? And I really can't think of, I'm trying to think of specific examples, but like to really pinpoint it, okay? And how you can, and this allows you to clearly identify weaknesses in like your argument, right? And allows you to think about like, what can I do next, okay? So like, here, let me actually use an example because I just thought of one. This is going to be an example from linear algebra, okay? So let's say that you have, this is a problem that came up in the Putnam seminar, okay? You had to compute the determinant. Actually, how many of you have linear algebra? That's okay. I think okay, that's fine. So you have to compute the determinant of this n by n matrix, okay, which satisfied these certain properties, okay? So the problem was, compute the determinant of this matrix. Basically, it looks like this. So this poor marker has been, there's no cap on it, so, okay. All right. So it looks like this. And then 1, 1/2, 1/2, 1/2, 1, 1/2, 1/3, 1/3, 1, 1/2, 1/3, 1/4, and then you get you really get 1/4, and then you go all the way down, and the last row is 1, 1/2, 1/3, 1/4, up to 1/n. You got to compute the determinant of this thing. Okay, it's pretty gross, right? And you have to find a general formula for this. Now, this is hard, right? So you look at this, you're like, I want to compute the determinant of this. This is super hard. I don't know what to do. I'm stuck. But what you need to really think about is, what is it specifically that makes this hard, right? Why are you getting stuck? The reason is because to compute the determinant of this general matrix, you need to use cofactor expansion. Well, you could put it in upper triangular or use cofactor expansion. But let's say you want to use cofactor expansion. Then to use cofactor expansion, you need to do like this times the determinant of this times the determinant of like this, right? It's way too computationally heavy. So the specific problem is not, oh, this is hard. The specific problem is doing cofactor expansion is too computationally heavy, okay? It's a very important clarification, because then you can think, how can I make cofactor expansion easier? How can I make cofactor expansion have less computation in total? And the answer is cofactor expansion is easier if you have a lot of entries which are 0 down a row or a column, okay? Because then you do 0 times the determinant of this, you have way less computation that you have to do. So basically the idea is, and that kind of brings you to the idea of the solution. So I'm not going to go through the solution, but you can, like for when you compute a determinant, you can replace one of the rows with, linear combo of the rows, and it doesn't change the determinant. So what you can do is like subtract this, subtract this one into this one and this one and this one. You can do a lot of subtractions and make like this column 0, for example, and compute it. That's a really terrible explanation of this problem, but I hope you understand the idea. Instead of just saying this problem is hard, you're pinpointing what is hard, and you're thinking about how can I fix this, right?
I gotta run.
All right, so yeah. Okay. Okay. So I think I'll be there. All right, I'm gonna go kind of lightning round. Okay. All right, because I want to talk about one thing at the very end. So proof structure, or no, information. Oh shoot, information storages. I'm gonna be really succinct with these because I always talk way too much. Information shortages. So if you're at a problem and you have a shortage, so here, let me look at what I wrote. When faced with a shortage of information, ask, have you deduced everything from the initial conditions, right? And have you used every piece of given information? Okay? Often the information that you're looking for is in the piece that you haven't used, okay, or you haven't considered. I'll skip that one. All right, on computation. Okay, so this is also important, on computation. So a lot of times in a proof, you're going to have to use some computation because you might need to figure out an answer, for example. Or maybe you need to evaluate some sum. That's going to require computation. So computation, first thing is, actually, you know what? I'm gonna talk about this one on its own. First one is be prepared. Okay? Be prepared for computation. So be ready for computation, okay? Because a lot of times it can take a long time and it can be hard. So a lot of times or sometimes you'll be able to say that, okay, I know how to figure out the solution. I could just bash this through and compute this and get the answer. But what you need to do is before you do that, properly gauge how long that might take, and then gauge whether continuing to search for another simplification is worth it. Okay? So there's this trade-off. So you could write a 6-page proof with a lot of computation and do it now, or maybe you want to take 15 minutes and maybe be able to write a 3-page proof. And you have to think, which is going to save you more time? Okay? Although in the end, you don't have to overthink that necessarily. Okay. So you got to be prepared. And if it's manageable, you should just go for it. Now, maintain direction. Okay? So whenever you start doing computation, it's very easy to just shut your brain off and just do it, right? But make sure that you're maintaining direction and you're thinking about what am I actually trying to figure out, right? And you also want to remain open the entire time. Okay, so stay open. Okay? Again, a lot of times when you do computation, it's easy to tunnel vision. I'm getting my chat blown up. Okay, all right. It's easy to get bogged down and just do it, just tunnel vision and do it. But you want to stay open because a lot of times when you're doing computation, when you're halfway done, you realize, oh, I can make this massive simplification and solve this, right? Here's an example, okay? Let's say that you, shoot. Let me think about this. Okay, here. So let's say you're doing computation and then you have to figure out 1/2. No, this is too complicated. All right, a good example is if you know what a telescoping sum is. Okay, actually, I'll just use it. Let's say, okay, you're doing computation. You have to figure out 1/2 times 1 plus 1/3 times 2 plus 1/4 times 3 plus 1/n times n plus 1. Okay, so you want to figure this out. Now, if you're in a sort of tunnel vision mindset, you might just be just try to bash this through or something, right? Just try to which would be dumb, okay? But if you stay open and you are still being creative and thinking of ideas, what you can realize is that you can actually split it up like this. split up each of these terms like this. And this actually becomes a telescoping sum because these terms cancel, these terms cancel, these terms cancel, and the answer is actually 1 minus 1 over m plus 1. Okay, so the point with this is that if you stay open when you're doing computation, often you can make this really massive simplification, and it'll save you a ton of time. So stay open when you're computing things. And the second is to mitigate errors. So another problem with rushing is that you're more likely to make an error. And an error in computation can be very bad, right? Because then you can get something which is wrong. Okay, so mitigate errors. Basically, the way you do that is make sure that you're also checking your work as you go along, right? Okay. Oh my God, it's already 1:30 or 1 hour, 30 minutes. Okay, I'm almost there. Okay. So a few more things. Now, number 10 is in proof structure. Okay, so this is how these are some tips I can give you on writing your proof. Okay, so, oh my God, okay, so there's a few things when you're writing your proof that can really make things simpler for you. The truth is writing, actually, if you've taken some theoretical math course, you know that writing a proof, oh my God, we got so many people going on in the chat. Okay, so one of the things you know about writing a proof is that just because you know like how to explain how to do something in a very vague way, writing the proof is actually like a whole nother thing. It's like a whole nother thing you have to think about and a whole nother skill. So here's just some things that I would recommend when you're writing a proof. Okay. So the first is look for simplifications of logic. Okay, so a lot of times, like let's say you solve the problem and you're like, okay, I'm gonna start working on the proof. You don't just want to turn your brain off. You want to keep looking for ideas because sometimes you can really simplify the logic of your proof, okay, by making another key idea. Remember, the best of the best are solving these problems and writing the proof in like 10 minutes, 10, 15 minutes. So if you stay open, sometimes you can find those ideas that really simplify it. The second thing is lemmas. Okay, now, does everyone know what a lemma is? Okay, a lemma is like an intermediate statement, right? An intermediate theorem, a mini theorem that you put at your proof, usually at the beginning. Lemmas are really good for organizing your proof. So if you ever have this big intermediate result, like in the middle of your proof, like, oh, like you need to compute something, then it's really good to just like shove that in like a little lemma at the beginning, and then later you can invoke it, okay? So like if you can break up your proof, then using lemmas, then it's good to do that, okay? Although, I mean, you kind of have to judge whether it's worth it. Okay, so, all right, so, all right, now last thing is end game. Okay, this isn't like, there's going to be one last thing I want to talk about after this, but end game. Okay, what do you do at the end of that 3-hour block? So this is my advice. Now, 2-hour 20-minute mark. Before the 2-hour 20-minute mark, you should just be not worrying about time. You should just be doing your best trying to figure out these problems, okay? Once you get to this mark, though, you only have 40 minutes left. So you have to think about, okay, what am I going to do, right? Like, is it better for me to get partial credit? Is it better for me to keep trying to pursue this problem, right? So this is where time actually becomes a factor. Before this, don't worry about time, okay? So here, what I'd recommend you do is this. At that mark, you have to make a decision. So what you want to do is you want to pick the problem that you think you have the best chance of solving, okay? And then all of the other things you thought about, all the other partial credit, write all that other partial credit, and then devote all your attention to that last problem that you think you have the best chance of solving, okay? And then at the 2 hour 40, like once you get to like 2 hour 45 minutes, you got 15 minutes left. It's good to just kind of write what you have. Although, like you may actually be closer than you think. Like you may be able to actually squeeze something out at the very end. So there were instances where like I had the solution like right under my nose and I didn't see it. Wait, there's one last thing. Okay, yeah. All right. Now, okay, so to finish this off, I'll talk about one last thing. 2 very quick last things. Thank you. I know this is a lot. Okay. So here, all right. So now these are techniques. So that was like problem-solving strategies, pretty broadly applicable, except the last one's kind of Putnam specific. Now this one has to do with like they're pretty mappy. So this one is what I call the algebraic process. Now, so this is a way that I approach a lot of problems, a lot of problems that involve like algebra, okay, which is basically all of them. The idea, like the way that you want to view this is like so let's say you have some equation, right? Some algebraic equation. Now you have many different things that you could do with that, okay, with that equation. If it's a Putnam problem, or well, usually you have a few things you could do with that equation, right? So you want to think about, okay, what are all the possible things I could do, right? And which one do I think is best? Which one do I think is going to get me to the solution? So it's like you have like this tree, right? So here's your initial equation. Then you could take, any of these 3 paths, for example. And then from here, if you do any of these things, you could take all these different paths, okay? So, I mean, this is why problem solving is hard, because there's so many things you could do. So this is kind of most people don't think of solving an algebraic equation like this. They usually don't think of it like this, like I'm here, what are all the possible things I could do? And they think of it like in this tree structure. What's good about this is that a lot of times there's only one thing that like really makes sense. So like if you have x plus 5 equal to 3, I hope everyone knows how to do this, okay? So if you have this equation, there's really only one thing that makes any sense to do, which is subtract 5 from both sides, right? Because if you're trying to isolate x, then you want to get rid of the plus 5, right? So like multiplying by 2 on both sides doesn't make sense. Adding things doesn't make sense. There's only one thing that makes sense. So a lot of times when you're, even with a really complicated equation, a lot of times there's only one thing that will make sense to do, and you should just do that, okay? So yeah, so basically this is just like a framework for viewing how to do algebra problems, okay? You want to think about, what are the things I could do, and then pick the one which is best. Okay, the second thing, and this is going to be the last strategy, induction and recursion. So induction and recursion is super powerful in the Putnam. Using induction is a very common strategy. And you don't want to think of induction as just like this proof technique. You want to think of induction as like this way of viewing how to solve the problem, like this mindset, okay? Because what you can do, like if you have this like inductive mindset, then let's say you're trying to figure out what A5 is, okay? You want to figure out let's say you want to figure out what A sub n is for a general n, and you're trying to figure out what A5 is. If you figure out that A5 has an A3 in that equation somewhere, then you can just like assume that you know how to do A3, even if you don't, right? Because the principle is that like what you're doing is you're thinking, okay, later down the road, I'm probably going to use recursion or induction. So like I can just assume that I know that, right? And I don't have to think about it, right? Until like much later, if that makes sense. I don't know if I explained that well. Basically, you can assume that you know lower cases. So it's like a mindset, not just like this proof technique. And this is very like wishy-washy, right? Which is not characteristic of the formal proof technique induction. Okay. So yeah, so induction and recursion is super useful. Okay. Now that's the last thing I'll talk about. Well, I keep saying the last thing. One last thing. the point system. So I just realized most people probably don't know how the scoring system works. Okay, so I thought I'd clarify that. So you can get 10 points. You can get anywhere from 0 to 10 points on any problem. Okay, see ya. You can get anywhere from 0 to 10 points on any problem, right? But you will never, and when I say never, I mean basically never, get any score other than 0, 1, 2, 8, 9, or 10. Okay? They don't give anything in the middle. So what that means is if you write a complete solution and maybe you miss a couple minor cases, then you might get a 9 or an 8. But if you get 80% of the way there, you get max a 2 out of 10. Okay? So what that means is basically getting a complete solution is significantly more points than getting a lot of partial credit. Okay? So whatever partial credit you get, usually you're going to get a 1 out of 10. So now that's still, 1 point is 1 point. On an exam where most people get max 1 point, that's good. But my point is, just keep that in mind, right? That's why, partial credit, you really shouldn't be too focused on that. Okay. Thank you, everyone who came. Damn. Okay, I know that was long. I know I said it was going to be an hour and a half. Oh, I need to read the comments, yeah. So yeah, the Putnam exam is Saturday. Thank you for coming. So biggest advice.
You didn't thank me for coming.
What? I did thank you. Biggest advice is, Friday night, don't turn up, get some good sleep, go to bed early, get good sleep, and come ready, come prepared to do some math.
Don't do stuff Friday night,
Yeah, I didn't say that. I just said, just go to sleep early. There's a difference. Okay. Don't get plastered Friday night. Don't be hungover during the Putnam. That'd be terrible. Okay, I have to read the comments before I end the stream.
Andrew, are you still on? Or Julie? I told Julie to come on because she was texting me. So
Okay. PogChamp in the chat. Okay. There's 2 people just watching me read the
shush,
chat.
Steven.
Steven, you look cute. Thank you, Andrew. Yes.
Exactly is the button of where do I show up on Saturday?
Oh, that is a great question. Where do you show up? You show up, if you're at Pitt, you show up in the math lounge, room 705. Oh yeah, right there. Yeah. Wow, you guys are being a little explicit. Steven, okay. Why am I being objectified? Huh? Huh?
Because.
Bella, you are biased. Okay. Kevin says 69 easy. Okay. Okay. All right. Yep. Thank you for coming.
Oh, you didn't get the little peach.
Okay.
I put a peach emoji.
All right. Thank you everyone for coming. That was really, my hand is, see?
Get back here so we can
And
talk
yeah, I need to talk about housing. So good luck on the Putnam if you're taking the Putnam. And yeah, make sure to smash like and subscribe as always. Bye.
Bye.
Bye.